If you recall, in an earlier video, we mentioned the angle of twist, which is the clear indication of the deformation of this shaft under applied torques. How do we determine this angle of twist? Again, if you still remember, when we were deriving the torsion formula, we got to this step. And also, according to Hooke's law, tau equals to G times gamma. G is the modulus of rigidity, which is the constant for a material. Gamma, again, is the shear strain. And also we know the torsion formula now, tau equals to T, the internal torsional moment, times rho, the radial position, over J, the polar moment of inertia of this entire cross-sectional area. Based on all these, we can derive that d phi equals to this, and then lastly t over jg dx. Therefore, if we want to find out the angle of twist of one end of this shaft, say end B, which is at x equals to L, relative to the other end, say end A, which is when x equals to 0, then the angle of twist of B relative to A equals to the integration of d phi along this entire length of the shaft from x equals to 0 to x equals to L, which equals to the integration of t over jg dx. Here, t again is the internal torsional moment, which is the function of position, j the polar moment of inertia, and g the modulus of rigidity could also be functions of a location, since sometimes there could be cross-sectional change in this shaft, or the shaft could be composite shaft made of several different materials with different G values. If you compare the torsional deformation to axial deformation that we learned earlier, there are many similarities, and hopefully this can help you memorize the equations associated with the torsional deformation. First thing first, the normal stress is defined as the normal force over cross-sectional area. The torsion formula can also be rewritten in this form. Here, the numerator T is also an internal reaction, which is the driving force for deformation, and the denominator J over C is the combination of geometric properties of the cross-sectional area. The axial deformation, delta B relative to A, the displacement of one end relative to the other, equals to the integration of N, which is the internal normal force, over A, the area, E, Young's modulus, integrated from one end A to the other end B. Angle of twist of one end B relative to A, again, equals to the integration of T, the internal torsional moment, over J, polar moment of inertia, which is a geometric property just like the area, and G, which is the modulus of rigidity, similar to Young's modulus, and again integrated from one end A to the other end B. And both equations can be reduced in this summation form if there are several segments, and within each segment, the internal reaction is a constant, geometric property is a constant, and the material property is a constant. And if you only have one segment with the constant internal reaction, constant geometric property, constant material property, then these two equations reduces to this simple form. Let's look at this example. For this composite shaft subject to multiple applied torques as shown, we need to determine the angle of twist of end D relative to the fixed end A. If we want to determine the angle of twist, we need to determine the internal torque as a function of position. And if you recall, we have done this in a similar example problem in the earlier video. And here's the result. Internal torque determined as a function of position, shown in this internal torque diagram. As you can see, here we do have three segments. Within each segment, the internal torque is a constant, the geometric property is a constant, and the material property is a constant. Therefore, we're going to use the summation form of the equation to determine the angle of twist. So we use the summation format of the equation to determine the angle of twist. substitute in all the values for the internal torsional moment, the polar moment of inertia of each segment, and the modulus of rigidity G for each segment. Keep in mind here, it's important that you keep those negative sign in the internal moment, because negative sign indicates clockwise rotation about the x-axis and positive sign indicates counterclockwise rotation about the x-axis. Therefore, when we do the calculation, the answer is negative 2.08 times 10 to the negative fourth power in the unit of radian. What does this mean? Since the angle of twist is determined to be a negative value, since we chose this to be our x-axis, therefore a negative angle of twist indicates a clockwise rotation about this x-axis. In other words, when compared to the fixed end A, end D has rotated clockwise to the right. Let's look at this example. For this cylindrical shaft subjected to the distributed torque as shown, we need to determine the angle of twist of end B relative to the fixed end A. In this case, the distributed torque is not uniform. It actually has a linear intensity given by the equation T equals to 120 minus X pound-inch per inch. But just like any other problem, we need to first determine the internal torque as a function of position X. Again, we start with the free body diagram of this shaft. Draw the unknown support torque at the fixed support TA, again drawn in the positive direction, counterclockwise. Moment equilibrium about the x-axis. Here, the resultant torque of this applied distributed torque is determined by integrating the torque intensity from 0 to the total length 120 inches. And from here, we can get TA equals to 7,200 pound-inch. Then we need to use method of section again to determine the internal torque as a function of position. We expose the unknown internal torque Tx, again drawn counterclockwise in the positive direction, and then we do the torque equilibrium about the x-axis. Here, the resultant torque of the applied torque during this segment from 0 to x is determined by the integration of the torque intensity from 0 to x. And from here, we can determine Tx as a function of x. For this problem, we have to use the general form of the angle of twist equation to determine the angle of twist of NB relative to NA. It's the integration from A to B of T, which is the internal torque as a function of position, over Jg. Both J and G in this case are constants. Therefore, we're substituting the number and do the integration and got negative 8.05 times 10 to the negative fourth power radian. And that's our answer. But what does that mean? Again, our chosen x-axis is in this direction. Therefore, a negative angle of twist indicates a clockwise rotation about this x-axis. In other words, the NB, when compared to NA, has rotated to the right.